So here I'm told I have a passive solar house that's losing heat to the outdoors at an average rate of 50,000 kilojoules per hour. So here's the heat transfer coming out. But the house is to be maintained at 22 degrees C during the whole winter night, which lasts 10 hours. Now inside the house, we have 50 glass containers, each containing 20 liters of water. And those glass containers with water are heated to 80 degrees Celsius during the day by absorbing solar energy. There's also a thermostat-controlled 15 kilowatt backup electric resistance heater that turns on whenever necessary to keep the house at 22 degrees C. So I'm going to draw that just like this. There's some work being done on the house, and that's the electrical work. So the question is, how long will the electric heating system need to run during the night to keep the house at 22 degrees C? And if we didn't have the electric heater, so if we didn't have the work being done by electricity here during the night, then if we didn't have the solar heating, how long would we have to run the electric heater to keep the house at 22 degrees C? So when I look at this, I think this is a first law type of problem because I'm having to add in some electrical work to maintain the house at 22 degrees C, and there's some heat loss going on. So there's some electrical power or electrical work, there's some heat transfer. Makes me think that the first law would be the right tool to apply here. If I'm going to apply the first law, I need to apply it to a system. So the system I'm going to choose is one that surrounds the house. And because that's what I'm interested in. I'm trying to maintain the house at 22 degrees C. And I've got the heat transfer going out, the electrical work coming in. So let me go ahead and write out the first law, and then we'll simplify it. So it's the change in total energy of the system is equal to the heat into the system. And I'm going to write it as plus the work done on the system, because I know that there's electrical work being done on the system rather than the house doing electric work on the surroundings. Okay, so let me then expand the change in total energy of the system. So the change in total energy of the system is going to be the change in internal energy plus the change in kinetic energy plus the change in potential energy of the system. But since the house isn't moving, it's not changing elevation, those terms are going to be zero. If you're fortunate, your house is staying put. And so we're just going to have the change in the internal energy of the system. But the change of internal energy of the system, we have a couple of things here. We have the structure of the house, like the wood, the brick, all of the elements within the house. We have the air inside the house. We also have these glass containers filled with water in there. So let me write those all out separately. So we have the change in internal energy of the, I'll just call it structure, plus the change in internal energy of the air, plus the change in internal energy of the water. Okay, so we have all of those things that comprise our system. Now, since the house is being maintained at 22 degrees C, the structure and air inside the house will be at the same temperature. So these will be zero because the temperature is not changing, right? Again, the reason these are zero is because the house is being maintained at 22 degrees C, so the temperature isn't changing in there. So the only thing that's changing then is the internal energy of the water. Now the internal energy of the water, we'll assume that the water is an incompressible substance, so we're going to write that as the mass of the water times the specific heat of the water times the change in temperature of the water. I've made a few assumptions here, so let me expand those out in just a moment. Let me just finish writing this out, and then I'll tell you some of the assumptions I made here. Okay, so one assumption I made in going from this step to this step, so this step to this step, is that the water is incompressible. So that means I can write the change in internal energy as so it's the mass times the specific heat times the change in temperature. Technically, if I should probably write this, well, let me just write it over here. So the change in specific internal energy would be the integral as you go from some initial temperature to some final temperature of the specific heat of the incompressible substance, which is in general a function of temperature times small change in temperature. So that's for an incompressible substance. If we assume the water is incompressible and the change in temperature is relatively small, then we can say that the specific heat really doesn't vary much with temperature. And so I'm going to leave it as a constant and then write this as just, so that's about equal to C times delta T if C is a constant. Right? And so that's what I've done in going from there to there. So I assume that water is incompressible and C is a constant. All right. And then this very last step, oh, the other thing I guess I assumed, I didn't really write this down, is I neglected the internal energy of the glass containers. I don't know how big the glass containers are, but I'm assuming that the mass of the glass containers is pretty small compared to the mass of the water. So I'll note that here as well. So the mass of the glass is much smaller than the mass of the water. So that's why I didn't include the mass of the glass containers here. So that was another assumption. And then, of course, going from here to here, I just expanded the delta temperature for the water, just the final temperature of the water minus the initial temperature of the water. Okay? And so let me then rewrite the first law with this in mind. So we have the mass of the water times the specific heat of the water times the final temperature of the water minus the initial temperature of the water is equal to the heat into the whole system plus the work done on the system. Now let me go ahead and address now the heat transfer into our system. In fact, what's happening is there's heat loss, so this quantity is going to be negative, and it's 50,000 kilojoules per hour, and we're told that we have to go all night for 10 hours. So the total heat loss will be this 50,000 kilojoules per hour times 10 hours. So let me put that here. So this will be minus 50,000 kilojoules per hour times 10 hours. Okay, so that's the heat transfer in. It's actually out, but that's fine. And then the electrical work, we're told that we have a 15 kilowatt backup electrical resistance heater. So let me write that down as well. So that work is going to be 15 kilowatts, and that's going to act over some period of time. We don't know what that is. We're trying to find out what that time is because we're only going to have to turn it on part of the time because we're also dealing with the contribution of the internal energy of the water here. Now, as far as this quantity, we have to find the mass of the water, the specific heat of the water, and initial, final, and temperatures of the water. Well, the initial temperature of the water we're given as being 80 degrees C. The final temperature of the water would be down to 22 degrees C. Right? The specific heat of water, we can look that up in a table. That's 4.179 kilojoules per kilogram Kelvin. So that comes from a table of specific heats for various substances. And you'd want to choose a specific heat that's pretty close to this range of temperature. So maybe the temperature of like 50 degrees C or something, somewhere in between these two. Just somewhere in that ballpark. We're assuming that this value doesn't change very much. As far as finding the mass of the water, here we're told we have 50 glass containers, each filled with 20 liters of water. So you'd have to do 50 glass containers, each with 20 liters of water. And then you'd have to convert that over to cubic meters. Let's do that. So let's see, 1 liter is 0.001 cubic meters per liter. And then multiply by the density of water, which is about 1,000 kilograms per cubic meter. So that's how much mass of water you would have. If you do that calculation, I think that comes out to be 1,000 kilograms. All right, so now we have everything we need for that equation. We can just solve it for delta T. And when you do that, you have to be a little careful of some unit conversions in there, but when you do that, you'll find that it comes out to be 4.8 hours. So when you have these glass containers filled with water that start off at 80 degrees C, you only need to turn on your electric heating for about just under 5 hours. Okay. Now, part B is how long would the electric heater run at night if the house didn't incorporate solar heating? So in that case, we wouldn't have this left-hand side, right? There would be no, if there's no solar heating, then you don't have any of the mass of the water here, so that this term just would be 0. You don't have that, right? So the whole left-hand side would be 0, and so in that case, you'd have 0 is equal to Q into plus work done on, and so you would end up having to do the following. You'd still have this for the work done on, and you'd still have this for the heat transfer, so then you could solve for the delta T in that case, and that comes out to be 9.3 hours. Okay, so you can see it makes quite a bit of a difference having the solar heated water containers in your house, so you don't have to do quite as much electrical heating. Okay, so just to recap, this was a first law problem. We made the house our system. We wrote out the first law, recognized that the change in total energy of the system really is just the change in internal energy of the water, which was given down here. We assumed water was incompressible with a constant specific heat. The heat transfer was just found by multiplying this by the 10 hours. The electrical work was just the power that we were given, the 15 kilowatts times the delta T, and the delta T is what we solved for. And then the second part of the problem, we didn't have the water in the system, so this part was gone, and so just the heat and work needed to be balanced. So that's what this term came. So that's how we found part B. Okay, we'll end the example there.